Lecture 1. Reversible and irreversible reactions. An irreversible reaction proceeds mainly in one direction. Reactants are converted into products and the reaction approaches completion. A reversible reaction is different. The products can react to form the reactants again. This means that both the forward and reverse reactions must be considered. For example, nitrogen gas and hydrogen gas can react to form ammonia. At the same time, ammonia can decompose back into nitrogen gas and hydrogen gas. At equilibrium, both reactants and products are present. Equilibrium does not mean that reactants and products are present in equal amounts. It means that the overall composition is no longer changing because the forward and reverse reaction rates are equal. A particle diagram of an equilibrium system should show both reactant and product particles inside the same closed container. Lecture 2. Dynamic equilibrium. The word dynamic is essential when describing equilibrium. At equilibrium, particles do not stop moving, and the reactions do not stop. Reactants continue to form products, while products continue to form reactants. The two reactions simply occur at the same rate. Because the forward rate is equal to the reverse rate, there is no overall change in concentration. Dynamic equilibrium requires a closed system. If matter can enter or escape, the composition may continue to change, and equilibrium may not be maintained. Imagine a sealed container containing nitrogen, hydrogen, and ammonia. The molecules collide continuously. Some collisions produce ammonia, while other collisions cause ammonia to break apart. The average number of each type of molecule remains constant, even though individual molecules are constantly changing. This microscopic activity makes equilibrium dynamic rather than static. Lecture 3. Forward and reverse rate graphs. A rate versus time graph clearly shows how a system approaches equilibrium. If the system begins with reactants only, the forward reaction rate is initially high because the reactant concentration is high. The reverse reaction rate begins near zero because almost no product is present. As products form, the reactant concentration decreases. Therefore, the forward reaction rate also decreases. At the same time, the product concentration increases, so the reverse reaction rate increases. Eventually, the two curves meet. From that point onward, the forward and reverse reaction rates are equal and constant. The system has reached equilibrium. The reaction rates are equal, but they are not zero. The point where the curves meet represents the time when equilibrium is reached. It does not represent a time when the reactions stop. Because this graph describes reaction speed, the vertical axis must represent reaction rate, not concentration. Lecture 4. Concentration time graphs. Now consider a concentration versus time graph. If the system begins with mostly reactants, the reactant concentration decreases while the product concentration increases. As the system approaches equilibrium, both curves become horizontal. A horizontal line means that the concentration remains constant. The equilibrium concentrations do not need to be equal. One substance may be much more abundant than another depending on the value of the equilibrium constant. The important point is that each concentration stops changing over time. If the system is disturbed, the curves may suddenly jump or gradually change. They will eventually settle at new constant values. Always check the axes before interpreting a graph. On a rate versus time graph, equilibrium is reached when the forward and reverse rates become equal. On a concentration versus time graph, equilibrium is reached when all concentrations become constant. Lecture 5. Reaction quotient Q and equilibrium constant K. The reaction quotient, Q, and the equilibrium constant, K, have the same mathematical form. The difference is when the concentrations or pressures are measured. Q can be calculated at any moment. K describes the system only at equilibrium and at a specific temperature. Comparing Q with K allows us to predict the direction of the net reaction. If Q is less than K, the system has too few products compared with the equilibrium composition. The reaction proceeds to the right and forms more products. If Q is greater than K, the system has too many products. The reaction proceeds to the left and forms more reactants. If Q is equal to K, the system is already at equilibrium, so there is no net shift. Comparing Q with K provides a quantitative method for predicting the direction of a reaction. Lecture 6. Writing Kc expressions. Begin with a balanced chemical equation. Place the equilibrium concentrations of the products in the numerator. Place the equilibrium concentrations of the reactants in the denominator. Raise each concentration to the power of its stoichiometric coefficient. Consider nitrogen gas plus 3 hydrogen gas molecules forming 2 ammonia molecules. Kc equals the concentration of ammonia squared divided by the concentration of nitrogen multiplied by the concentration of hydrogen cubed. Include gases and aqueous substances in the Kc expression. Do not include pure solids or pure liquids. Their effective concentrations remain constant, so they are already included in the value of K. For example, solid calcium carbonate decomposes to form solid calcium oxide and carbon dioxide gas. In this equilibrium expression, only carbon dioxide is included. Always balance the chemical equation first. Changing a coefficient changes an exponent, which changes the value of K. Lecture 7. Writing Kp expressions. Kp is used for gas phase equilibria. It is written using equilibrium partial pressures. The structure is similar to a Kc expression. Place the partial pressures of the gaseous products in the numerator. Place the partial pressures of the gaseous reactants in the denominator. Raise each partial pressure to the power of its stoichiometric coefficient. For the ammonia reaction, Kp equals the partial pressure of ammonia squared, divided by the partial pressure of nitrogen, multiplied by the partial pressure of hydrogen cubed. The partial pressure of a gas can be calculated by multiplying its mole fraction by the total pressure. Kp includes gaseous substances only. Pure solids and pure liquids are omitted. Aqueous concentrations are used in Kc expressions instead. Keep pressure units consistent throughout the calculation. Lecture 8. Calculating Kc from equilibrium data. When equilibrium concentrations are provided, calculating Kc is straightforward. First, write the correct equilibrium expression. Then, substitute the equilibrium concentrations, apply the exponents, and calculate the result. Consider hydrogen gas plus iodine gas forming 2 hydrogen iodide molecules. Suppose the equilibrium concentration of hydrogen is 0.20 molar. The equilibrium concentration of iodine is also 0.20 molar. The equilibrium concentration of hydrogen iodide is 0.80 molar. Kc equals 0.80 squared divided by 0.20 multiplied by 0.20. The result is 16. Common mistakes include using initial concentrations instead of equilibrium concentrations, forgetting the exponent on hydrogen iodide, and using inconsistent units. Always write the symbolic equilibrium expression before substituting the numbers. Lecture 9. Calculating Kp from partial pressures. Calculating Kp is similar to calculating Kc, but equilibrium partial pressures are used instead of concentrations. Consider 2 sulfur dioxide molecules plus 1 oxygen molecule forming 2 sulfur trioxide molecules. Kp equals the partial pressure of sulfur trioxide squared divided by the partial pressure of sulfur dioxide squared multiplied by the partial pressure of oxygen. Suppose the equilibrium partial pressure of sulfur dioxide is 0.40 atmospheres. The partial pressure of oxygen is 0.20 atmospheres. The partial pressure of sulfur trioxide is 0.60 atmospheres. First, square 0.60. This gives 0.36. The denominator is 0.40 squared, multiplied by 0.20. This gives 0.032. Dividing 0.36 by 0.032 gives 11.25. Check that every exponent matches the coefficient in the balanced equation. Lecture 10. Interpreting the magnitude of K. The size of K describes the equilibrium position. If K is much greater than 1, products dominate at equilibrium. The equilibrium position lies toward the products. If K is much smaller than 1, reactants dominate at equilibrium. The equilibrium position lies toward the reactants. If K is close to 1, significant amounts of both reactants and products are present. K describes the relative amounts of reactants and products. It does not describe the reaction speed. A reaction can have a very large K and still proceed slowly if it has a high activation energy. A fast reaction can also have a small K and quickly establish a reactant-favored equilibrium. A large K means that products are thermodynamically favored at equilibrium. It does not mean that the reaction is fast. Lecture 11. Reversing and scaling reactions. Equilibrium constants change in predictable ways when a chemical equation is changed. If a reaction is reversed, the new equilibrium constant is the reciprocal of the original constant. In other words, the new constant equals 1 divided by k. If every coefficient is multiplied by a number, the new equilibrium constant equals the original k raised to that power. If every coefficient is divided by a number, take the corresponding root of k. For example, suppose a reversibly forms B and k equals 4. For the reverse reaction, B reversibly forms A, and the new k equals 1/4. If every coefficient in the original reaction is doubled, the new equilibrium constant is 4 squared, which equals 16. The chemical equation and its equilibrium constant are directly connected. Any change to the equation must also be reflected in the value of k. Lecture 12. Combining reactions and equilibrium constants. When chemical equations are added to produce an overall reaction, their equilibrium constants are multiplied. Suppose a reversibly forms B with an equilibrium constant called K1. B then reversibly forms C with an equilibrium constant called K2. When these equations are added, B cancels. The overall reaction is a reversibly forming C. The overall equilibrium constant equals K1 multiplied by K2. If a reaction must be reversed before the equations are added, first take the reciprocal of its equilibrium constant. If a reaction must be multiplied by a number, first raise its equilibrium constant to that power. After making these adjustments, multiply the equilibrium constants together. Lecture 13. ICE table setup. An ICE table organizes equilibrium calculations. ICE stands for initial, change, and equilibrium. Write each reacting substance in a separate column. In the initial row, enter the starting concentration or partial pressure. In the change row, use x and the stoichiometric coefficients to show how each amount changes. When the net reaction proceeds forward, reactants decrease, so their changes are negative. Products increase, so their changes are positive. Consider one molecule of gas, a reversibly forming two molecules of gas B. Suppose the initial concentration of A is 1.00 molar, and the initial concentration of B is 0. The change in A is negative x. The change in B is positive 2x. The equilibrium concentration of A is 1.00 minus x. The equilibrium concentration of B is 2x. These equilibrium expressions are then substituted into the equilibrium constant expression. Lecture 14. Kc ICE table calculation. Consider gas A reversibly forming two molecules of gas B. Kc equals 4.00. Initially, the concentration of A is 1.00 molar and the concentration of B is 0. The ICE table gives an equilibrium concentration of 1.00 minus x for A and 2x for B. The equilibrium expression is Kc equals the concentration of B squared divided by the concentration of A. Substitution gives 4.00 equals the quantity 2x squared divided by 1.00 minus x. Solving the quadratic equation gives the physically valid answer, x equals 0.618. Therefore, the equilibrium concentration of A is 0.382 molar. The equilibrium concentration of B is 1.236 molar. Reject any mathematical answer that produces a negative concentration. Finally, substitute the equilibrium concentrations back into the Kc expression to verify the answer. Lecture 15. Kp ICE table calculation. ICE tables can also be used with partial pressures. Consider hydrogen gas plus iodine gas forming two hydrogen iodide molecules. Write the initial partial pressures in the first row. If no hydrogen iodide is initially present and the reaction proceeds forward, the partial pressures of hydrogen and iodine each change by negative x. The partial pressure of hydrogen iodide changes by positive 2x. The equilibrium partial pressure of hydrogen is its initial pressure minus x. The equilibrium partial pressure of iodine is its initial pressure minus x. The equilibrium partial pressure of hydrogen iodide is 2x. Substitute these expressions into the Kp equation and solve for x. Confirm that every equilibrium pressure is positive. Also confirm that x does not exceed the initial pressure of either reactant. The chemistry and stoichiometry are the same as in a Kc ICE table. The only difference is that partial pressures are used instead of molar concentrations. Lecture 16. Particle diagrams in Q. Particle diagrams can be used to estimate relative concentrations when all containers have the same volume. Count the number of particles of each substance, then use these numbers in the reaction quotient expression. Consider nitrogen gas plus 3 hydrogen gas molecules forming 2 ammonia molecules. Q is proportional to the number of ammonia particles squared divided by the number of nitrogen particles multiplied by the number of hydrogen particles cubed. After calculating Q, compare it with K. If Q is smaller than K, the diagram contains too little product. The net reaction proceeds forward. If Q is larger than K, the diagram contains too much product. The net reaction proceeds backward. If Q equals K, the mixture is at equilibrium. Remember that particle counts are not coefficients. The coefficients become exponents, while the particle counts represent the current relative amounts. Lecture 17. Le Chatelier's principle and concentration changes. Le Chatelier's principle states that a system at equilibrium responds to a disturbance by shifting in the direction that reduces the disturbance. Consider A plus B reversibly forming C. Adding A increases the denominator of Q. Therefore, Q becomes smaller than K. The system shifts to the right, consuming some A and producing more C. Removing C also makes Q smaller than K. The system shifts to the right to replace some of the removed C. Removing A makes Q greater than K. The system shifts to the left, producing more A and B. Adding C also makes Q greater than K, so the system shifts to the left. A useful general rule is that adding a substance causes the system to shift away from that substance. Removing a substance causes the system to shift toward that substance. However, comparing Q with K provides the clearest mathematical explanation. Lecture 18, Pressure, Volume, and Inert Gases. For gas phase equilibria, changing the volume changes the partial pressures of all reacting gases. Decreasing the volume increases the pressure. The equilibrium shifts toward the side with fewer moles of gas. Increasing the volume decreases the pressure. The equilibrium shifts toward the side with more moles of gas. Consider 2 sulfur dioxide molecules plus 1 oxygen molecule forming 2 sulfur trioxide molecules. The reactant side has a total of 3 moles of gas. The product side has 2 moles of gas. Compression shifts the equilibrium to the right. Expansion shifts the equilibrium to the left. If both sides have the same total number of moles of gas, changing the volume does not cause an equilibrium shift. Adding an inert gas at constant volume increases the total pressure. However, it does not change the partial pressures of the reacting gases. Therefore, Q does not change, and the equilibrium does not shift. Always distinguish between total pressure and the partial pressures of the reacting gases. Lecture 19. Temperature and the value of K. Temperature is special because it is the only common disturbance that changes the value of K. Treat heat as either a reactant or a product when predicting the direction of the shift. For an exothermic forward reaction, heat is a product. Increasing the temperature adds heat, so the equilibrium shifts to the left and K decreases. Decreasing the temperature removes heat, so the equilibrium shifts to the right and K increases. For an endothermic forward reaction, heat is a reactant. Increasing the temperature causes the equilibrium to shift to the right and K increases. Decreasing the temperature causes the equilibrium to shift to the left and K decreases. Heat is not included in the written equilibrium expression. However, changing the temperature changes the numerical value of K. Concentration changes, pressure changes, and catalysts do not change K when the temperature remains constant. Lecture 20. Catalysts and Q compared with K. A catalyst lowers the activation energy of both the forward and reverse reactions. Both reactions become faster, so the system reaches equilibrium more quickly. However, a catalyst does not change the energies of the reactants or products. It also does not change the standard Gibbs free energy change, the value of K, or the equilibrium composition. If the system is already at equilibrium, adding a catalyst does not cause a shift because Q remains equal to K. If the system is not at equilibrium, comparing Q with K still determines the direction of the net reaction. The catalyst only changes how quickly the system reaches equilibrium. On an energy diagram, the catalyzed pathway has a lower activation energy peak in both directions. The starting and ending energy levels remain unchanged. Lecture 21. Saturated solutions and KSP. A slightly soluble ionic solid can establish a dissolution equilibrium with its ions. In a saturated solution containing undissolved solid, dissolution and precipitation occur at equal rates. Consider a general ionic solid that produces M cations and N anions when it dissolves. Ksp equals the cation concentration raised to the power of M, multiplied by the anion concentration raised to the power of N. The pure solid is not included in the expression. If Qsp is less than Ksp, the solution is unsaturated and more solid can dissolve. If Qsp equals Ksp, the solution is saturated and at equilibrium. If Qsp is greater than Ksp, the solution is supersaturated. Precipitation occurs until Qsp becomes equal to Ksp. Lecture 22, Molar Solubility and Ksp. Molar solubility is represented by S. It is the number of moles of a solid that dissolve per liter to form a saturated solution. Stoichiometry connects the molar solubility to the concentrations of the ions. Consider calcium fluoride. One formula unit of calcium fluoride produces 1 calcium ion and 2 fluoride ions. If the molar solubility is S, the calcium ion concentration is S, and the fluoride ion concentration is 2S. The Ksp expression equals the calcium ion concentration multiplied by the fluoride ion concentration squared. Substitution gives Ksp equals S multiplied by the quantity 2S squared. This simplifies to 4S cubed. Do not assume that every ion concentration is equal to S. Use the balanced dissolution equation to determine the correct multiple of S for each ion. Then apply the correct exponents in the Ksp expression. Lecture 23. Predicting precipitation with Qsp. To predict whether a precipitate will form after two solutions are mixed, calculate the ion concentrations after mixing. Do not use the original concentrations directly. Account for the new total volume first. Then calculate Qsp using the same mathematical expression as Ksp. Compare Qsp with Ksp. If Qsp is less than Ksp, the solution is unsaturated and no precipitate forms. If Qsp equals Ksp, the solution is exactly saturated. If Qsp is greater than Ksp, the ion product is too large and a precipitate forms. Ions are removed from the solution in the stoichiometric ratio of the solid until Qsp becomes equal to Ksp. Dilution usually decreases the ion concentrations and lowers Qsp. Dilution can make a saturated solution unsaturated. If undissolved solid is present, more of the solid may then dissolve. Lecture 24. The common ion effect. The common ion effect occurs when a soluble compound adds an ion that is already present in a dissolution equilibrium. Consider calcium fluoride dissolving to form calcium ions and fluoride ions. Adding sodium fluoride increases the fluoride ion concentration. Immediately after the addition, Qsp becomes greater than Ksp. The system shifts toward the solid. More calcium fluoride forms and less calcium fluoride remains dissolved. The molar solubility decreases, but Ksp remains constant because the temperature has not changed. In a calculation, include the initial concentration of the common ion in the ice table. If the initial common ion concentration is much larger than the additional concentration produced by dissolution, an approximation may be used. However, the approximation should always be checked. The main idea is simple. Adding a common ion shifts the equilibrium toward the solid and decreases the solubility.